that can be done there. So this is the group of people that were involved in doing that. So the co-PI team were Miriam Benesty, Stefano Fucini, Mizuto Fukugawa, Christoph Punt, and myself. And then there's this huge group of researchers that were helping along with that. So there's a huge amount of junior researchers in there. So that was something that we're particularly proud of with this collaboration, just the sheer number of junior researchers involved in it, and who really led, I'd say, the bulk of the work here. So I think we're all familiar with these sort of images of protoplanetary disks. Programs like D-Sharp have really shown that the millimeter dust, the grains that we're tracing through their thermal emission, show an exquisite level of structure within these disks. They're primarily structured in gaps and rings, but we have seen a handful where we see azimuthal variations, such as HD 135, 344b, or a number of different ones. And these sort of observations are fantastic because they really show you sort of a detailed picture of the structure of the disk. It's very hard to do better in terms of angular resolution and sensitivity than you can with continuum data. The problem is continuum, or the dust grains specifically, are not really tracing the bulk processes within the disk. They're really reacting to what the gas is doing. So what we want to do is to understand what's sculpting the dust, what's causing these sort of structures. And to do that, we need to look at the gas distributions within these disks. And so in parallel to this really incredible transformation in our ability to map the dust, we've had a similar transformation in our ability to map the gas in these systems. So this is perhaps a pretty unfair comparison, but this is sort of our view of HD 163296 prior to ALMA. This is data from the SMA, and you can see in the bottom left, we've got these large beams. It's sort of washing out a lot of the signal, but you can see this overall pattern of Keplerian rotation, this sort of butterfly morphology that moves from one side of the disk to the other with different frequencies. Then ALMA came along, and we have a completely different view of this disk now. So you can see the change in angular resolution down here in the lower left. We're just absolutely overloaded with detail in these sort of observations. You can now see both sides of the disk. You can see that they're vertically extended. You can see that there's variations in the morphology of the emission here. And so we're just working with a huge amount more information about what the gas is doing, thanks to this increase in angular resolution. ALMA didn't technically bring a similar step in our ability to record information at a higher spectral resolution, but the sensitivity of ALMA allowed us to actually image it and really leverage the fact that we can spectrally resolve these lines. And so not only look at the distribution of the emission morphology, but understand the gas dynamics underneath that as well. So we're getting this 6D phase space information about what the gas is doing, and that's going to really help us understand what was causing the structures that we see in the dust. There's already been a handful of surveys that have been looking at the gas distribution, and MAPS is one of the most notable examples. The program looked at just 5 disks, but looked at them in a range of different molecules. And what was pretty striking was that the distribution, or the emission distribution within the same disk for different molecules, can look wildly different. So again, this is HD 163296, and we're just looking at the integration intensity here. And you can see, depending on the molecule that you're looking at, you see very different morphologies. Things like C2H show these really nice, well-defined ring structures. The CO isotope logs just seem to be everywhere. They don't show a lot of underlying structure. We see some that are very small and compact, very close to the star, and then we see some that are much more extended. And so it's great that we're seeing all this complexity in the morphology. That means we've got a lot to learn from the data. But it poses the question of whether these structures that we're seeing are driven by the chemical or physical variations. And that's really quite a hard thing to disentangle without a lot of forward modeling, which can be sort of computationally expensive and sort of driven by a lot of assumptions from your model. The way that we've been thinking about this is that those spectrally resolved observations allow us now to look at the kinematic structure of the disk, how that gas that is emitting is moving. And so we can now map out the sort of gas velocity structure to really exquisite detail. I'd say that with several different techniques, we can get down to a precision of around 10 meters per second for the integrated line of sight velocity. And that allows you to drive maps that look something like this. So this is the TW Hydra disk and the velocity structure that we infer based on the 12CO, and then from the much weaker and less abundant CS. But you can see we have the sort of standard dipole moment, we've got the red shifted side, the blue shifted side, and this in principle gives us a really powerful way to start looking at the processes within the disk. One of the most standard ways that we've done this is just by simply modeling this rotation pattern as we see as purely Keplerian or purely rotational, subtracting that and revealing a number of structures beneath that. So prior to exoALMA, there was, again, a handful of sources where we've been able to do this. And we showed that when we measure the velocity structure with this sort of detail and subtract away a background sort of purely rotational model, we're left with these really complex structures. This gallery shows just a few of the examples that we're seeing. On the left, we have HG100-546, which had this, what was coined a Doppler flip, this red and blue residual very close together. HG100-453 and TW Hydra both show these sort of spiral arm shapes. So spirals are not something that we tend to see in dust at all, but it seems to be quite common in the gas velocity structure at least. And MWC480 show these really nice sort of annular rings, so regions where you have what we think is vertical motion upwards and then downwards in this sort of corrugated structure. So with all this information to hand, we developed the exoALMA program to really answer the question of how common is this velocity structure in the disk as well. If we do this to a much larger sample of disks, do we see any commonality between them? Do we see common structures? Can we see evidence of embedded planets? Can we use the dynamics as a way to better understand the physical structure of the disk? And so we convened exoALMA. Again, here's a big list of everyone involved and a couple of photos of the collaboration. So this was almost a 5-year program in the end. COVID sort of slowed things down, but as people started being able to travel again, we were able to host workshops and collaboration visits where we came together and really worked with the data and tried to understand it all. So again, I want to highlight the fact that this was really, I think, driven by the junior researchers in the program. A lot of the more senior folks were able just to sit back and watch the incredible results roll out from these sort of PhD students working with the data. And the end result of the program was observations that looked something like this. So this is a gallery of the 12CO peak intensity for our 15 sources. You can see already, hopefully, that there's a variety of structures that you can just see in the moment zero map. So you can see that there's some variations for these annular structures. You can see that there's spiral arms in there. You can see that there's this sort of diffuse outer band that we see in a number of different sources. And if you're familiar with it, you can see that many of them do show the hallmarks of being vertically extended disks. You can see this sort of donut or bagel shape like morphology. And so it wasn't just 12CO that we're able to observe. We also observed 13CO and CS. These three molecules were observed at band 7 because we wanted to try and get the highest velocity resolution we could. So the data was taken at a resolution of around 27 meters per second, although most of the work that we used actually imaged it at a slightly coarser resolution. So in principle, you can go back to the data and image these at a much higher velocity resolution than we have for this first wave of papers. The choice of those 3 lines is really to try and offer us an opportunity to look at the vertical structure of these disks. Our idea was that the 12CO was tracing nearer the atmosphere, 13CO slightly further down, and CS below that again. And so this is something that Maria is going to talk a lot about later. So all this data is really a huge challenge to try and make sense of, trying to understand what we wanted to do with it and what stories we wanted to tell. And so this resulted in the 17 papers that came out from this first wave of papers. And I'm going to try and talk through, I think, some of the major findings. I can't do all of them justice within 45 minutes, but I want to try and highlight a few of the major science themes that came out of this first wave. Before I dive into what I would call the science that came out of it, I really want to highlight these 5 papers that did a huge amount of the foundational work that really facilitated us being able to do that science. So these are papers that looked at the methods and the techniques that we used, made sure that they were as good as they could be, and made sure that we were able to extract as much information as we could from that data. So often these papers, I think, get left behind because they're not really highlighting the really exciting new science findings, but they are really fundamental to being able to produce those science results. So exoALMA 2 was led by Ryan Loomis, and that was looking at the imaging and calibration of the data. If any of you have worked with ALMA data before, you know that this is quite a painful process. And so Ryan has really laid out in quite a nice way how we have calibrated and imaged our data. And if you go onto our website, exoALMA.com, you can get access to all the imaging and calibration scripts for yourself, so you can reproduce our workflow on any sort of data set that you have. exoALMA 3 was led by Andres Izquierdo, and he is the core developer of DiskMiner. This is a tool that I'm sure many people here are familiar with. And this was really the backbone to a lot of the analysis that we do. And I have a slide on that later on. But basically, Andres's tool took us from the images that we're able to obtain to the data products that we needed to really analyze and test our models. Jehan Bey led exoALMA 7, which was the numerical code and RT benchmark. This was quite a painful process, so I'm really thankful for Jehan for leading that. And the goal of this paper was really to take all the different codes and simulations that we were using as part of exoALMA, run a benchmark, and make sure that they were all producing consistent results. So when it came to analyzing our data, we were confident that no matter which code we were using to interpret those results, they would all give the same result. And so exoALMA 7, I think, is a really powerful paper for just giving us confidence in the results that we're returning. exoALMA 8 and 9 are two sort of similar papers that are looking at different ways that we can describe the emission morphology that we're seeing. So exoALMA 9, led by Brianna Zawadzki, was looking at regularized maximum likelihood imaging. So this is an alternative to clean, which is how we generally image interferometric data. And in here, Brianna was looking at a different approach and trying to make sure that the features that we're retrieving from these images, which can be fraught with sort of systematics due to the imaging process, are robust. And so again, she's imaged a number of the sources in our sample. All those data are available, and you could compare directly the maximum likelihood images that she derived with our Teague images. And exoALMA 8, led by Tom Hilder, was looking at a similar sort of modeling technique where once you have this image, how can you generate a really flexible model of the emission morphology and use that to better understand the correlated noise within your data. So this is something that I don't think we do as a community as well as we should. We often treat the noise as independent. We just take pixels that are, say, a beam full width half maximum apart and treat them as independent. That's not really right. And Tom's done a really great job of trying to quantify that much better and understanding how that imaging process really influences those results. So as I say, DiskMiner was really the backbone for a lot of what we were doing. This is available on Andres's GitHub. Again, if you go to the exoALMA website, there's a link to all the different software that we used, so you don't have to remember the URL here. But to just give a brief view of what DiskMiner was doing, because that really sets up the rest of the talk, DiskMiner was trying to model all the channel maps that we had. So the emission at different frequencies throughout the observations, and trying to model them simultaneously with basically a sum of different Gaussian components. So this is the flowchart for what DiskMiner does. Top left, we start with our observations, the channel maps. It first asks, is the backside visible? So as I mentioned before, with this resolution we have access to with ALMA, we can see emission from the front and the backside. If we see the front and backside, then we have to model that as two components, one accounting for each side. Otherwise, we can just use a single component because we're only seeing the front side for face-on sources. It can then model this full disk structure to create model channel maps, which you see in the top right, which allows to then extract properties of the data from. So we're looking at, say, the moment maps of the velocity structure of the top side and the bottom side. We can look at how the peak intensity varies as a function of radius, how the line width varies as a function of radius. We can look at the decomposition of the velocities, so the rotational, radial, and vertical components, and so on. So DiskMiner is a hugely powerful tool, and as I say, it really was the backbone to a lot of the analysis here. And I'd really recommend people going out to check out this code if you wanted to look at similar sort of data yourself. So as I mentioned, I wanted to try and distill all the 17 papers that we have into some major science themes, so to fit it in a 45-minute talk. And I think there are three directions that these exoALMA papers have made a significant leap forward in. And so that's basically defining the recipe for making planetary systems. We're looking at the ingredients, sort of what materials are available for making planets, the methods, how we combine those materials, so bring it from a disk sort of distribution within a disk into, say, environments that are making planets themselves, and then thinking about the outcome. What are the actual planets looking like? Where are they forming? Do we see evidence of those planets within these disks? So the first one we're going to talk about is the materials. What materials are available to form planetary systems? Now, I'm sure everyone here is well aware of the problems and challenges associated with trying to measure the mass in a protoplanetary disk. This figure from Anna Miatello's PP7 review chapter, I think, really nicely highlights it, that even for one of the most well-studied sources, TW Hydra, we have a huge range of inferred disk masses, depending on the methods that you use or the particular traces that you're using. And so in principle, while this order of magnitude or two spread in masses is probably okay on a sort of a population level, if you really want to understand the planet forming ability of a particular system, you really want to know whether you're on the left hand of this figure or on the right hand of this figure. And the real issue comes down to the fact that the dominant constituent of the disk, molecular hydrogen, does not emit radiation effectively at the low temperatures of the disk. So we're basically having this invisible component of material. Now, we know as a community how to solve this problem. We've come into this issue before. If we're not able to see that matter through the radiation, we can see that matter or infer its presence through its influence on the dynamics of the system. So I'm talking here about the dark matter component of galaxies. We can't see that through the radiation, but we can see how it perturbs the rotation curve of those galaxies. And this is some of the work showing that from Vera Rubin, where she was plotting the rotational velocity of these galaxies and showing you that they sort of have this very distinct profile where they rise up and then plateau later on. And the only way to account for that sort of plateau that you're seeing was including a dark matter component, this gravitational potential that we can't see, in order to explain the dynamics. And so it's this technique that we can actually use to infer the masses of the protoplanetary disks when we have a precise enough rotation velocity and the disks themselves are massive enough. So this was work that was really pioneered from the Milan group. There's a handful of really incredible papers that have come out from there showing you how we can do this with disks. And there's been a handful of other different studies looking at really sensitivity of this technique. And so the challenge really comes down to the fact that we need to disentangle the pressure support from the disk. Unlike dark matter, which is collisionless, we're looking at the fluid, so we have to account for the pressure. You have to just decompose that pressure component from the self-gravity component. But it looks like for the most massive disks, so disks that are generally 5% of the stellar mass, we can get a pretty robust constraint on the total disk mass. So that's what I'm showing you here. This is work from Sean Andrews that did one of these systematic studies, showing you basically the inferred mass of the disk relative to the true mass of the disk. And with the different colored lines, the disk mass relative to the star mass. And so you can see as you get sort of above 5%, you sort of get a pretty tight posterior, where you're getting a really both an accurate and a precise measure of the disk mass. And so this was very similar to another report paper from the Milan group that found very similar limits. So this bodes incredibly well. It shows that if we can measure the rotation profile for massive disks very precisely, then we have a really robust handle on the amount of gravitational potential and therefore mass in these disks. And so this is what Joe Stadler and Cristiano Longorini set out to do. Joe was in charge of measuring the rotation profiles in these disks, and I'll talk a little bit about them later on. And then Cristiano was interpreting them along with the thermal structures that Maria obtained in order to try and derive constraints on the dynamical mass of these disks. What I'm showing you in this figure is an example of the sort of velocity profiles that we're able to extract from our data. I believe this is for the calcium-15. The blue and the green represent the rotation curves inferred for 12CO and 13CO, respectively. And what I'm plotting on the y-axis is not the absolute rotational velocity, but the rotational velocity when you subtract away some mean background rotation. The fact that you're seeing sort of structure in there is showing you that we're seeing the effects of pressure support and a non-uniform pressure throughout the disk. But Cristiano was able to show that we can really well reproduce these rotational profiles when we include the pressure support and the self-gravity component. And so for these 12 disks that were massive enough and sort of inclined enough that we could do this robustly, we're able to get very precise dynamical mass measurements of the disk. And we didn't have to assume anything about the rescaling of some trace components up to the full disk mass. We're tracing the mass directly, which I think is really fantastic. We're also able to put those results into context thanks to this work by Leon Chapman. So Leon was able to get additional data, basically looking at C18O and N2H+ for all our sources. So this is typically the combination that people are using to measure disk masses on larger population levels, where it's believed that the N2H+ can break some degeneracy in the CO depletion. And so we wanted to compare how those sort of masses would compare to the dynamical ones that we got. And so we can see there's quite some spread, which is perhaps not unexpected. We see generally that the gas to dust ratio is much higher than the canonical 100. So we're seeing a gas to dust ratio of around 400. This probably points towards the dust simply being optically thick. So this dust ratio was derived when we don't have any optical depth there. So this is really showing you that those rings and the structures that we're seeing in the dust have to be optically thick. And I think that's something that everyone would be okay with. We also see that there's quite a scatter in the masses derived, say, from the chemistry approach to the dynamical approach, with variations of up to 30 times difference between the two. And using the chemical models that make these mass predictions, we could move back and see where that discrepancy was coming from. And it looks like that the difference arises from the assumptions on the mid-plane cosmic ray rate. When you change the ionization rate within the disk, obviously that's going to impact the N2H+ flux. And so the wiggle room that we have in that ionization rate is enough to account for the difference that we see between the dynamical masses and the chemical masses. So although at the moment we might have some discrepancy between the two, I think there's a very clear path forward for how we can calibrate this approach if we have a better handle on the ionization structure. And then we can use this CO and N2H+ method on all the other sources that we are unable to do for the dynamical masses and really get robust mass measurements from all the disks. And so I think that's a really exciting prospect. Finally, Giovanni Rizzotti was able to look at the vertical structure of the disks, and using the dynamical masses that we derived as sort of an anchor point, he was able to look at how vertically extended different CO isotope logs were in the disk to try and understand the level of CO depletion within those disks. It's sort of very naive, you can think about that if there's more depletion in the disk, you're going to find things squashed together, compared to if there's less depletion, those layers should be more vertically extended. And this figure is showing you all the different CO depletion factors that Giovanni inferred for our sources. So this is relative to the standard 10 to the -4 that's assumed for the ISM. And you can see that we're seeing depletion factors of between 10 and 100, which is very similar to this range that was inferred for MAPS. So I think we're seeing sort of very similar factors there. So in terms of the ingredients, I think we're in a really exciting position because we've shown that for the most massive disks, so those that have disk masses greater than around 5% of the host star, which is around 5% of the sources that we can observe, we're able to measure masses pretty robustly. Using those as a comparison, we see that within our exoALMA sample, we would infer gas to dust ratios of around 400. That's higher than the 100, likely because of continuum optical depth. And we see there's a variation in the masses that would infer based on the CO and N2H+ method relative to our dynamical one. However, we think that can be calibrated with a better handling of the ionization structure. And finally, we see that CO is depleted relative to the ISM by a factor of 10 to 100, and that's sort of consistent with previous results. So we've got a really big step forward in our understanding of how much material is within the disk. And we can see that these disks are massive and they've got enough material to make planets. But how do we combine those materials? What are the processes that is taking us from the gaseous disk into the planets that we see? So in very broad brushstrokes, what we need to do is concentrate that material. It's all well and good if it's distributed in the disk, but we need to sort of speed things up like a chemical reaction. We need to increase the pressure, and we do that by concentrating the dust within these disks. And the idea here is that if we can increase the dust concentration to such a level, you get an incredibly high dust to gas ratio. You can incite something known as a streaming instability, and that will very rapidly grow your millimeter grains up to these planetesimal sizes. We see evidence of perhaps grain trapping and concentrating already happening in these systems. So we saw right from the D-Sharp survey and the TW Hydro observations that the dust is primarily in these rings. And so there's something that's forcing the dust together and concentrating it in these annular structures. And Sebastian Stammler had this really neat idea after the D-Sharp set of papers where the similarity in the optical depths that were inferred for these rings across multiple systems all pointed towards the fact that there was some regulating process within these rings that allowed them to concentrate a certain amount of dust before it disappeared or it stopped radiating at the frequency that we're observing at. And Sebastian argued that this is perhaps the onset of the streaming instability, that these rings are bringing in enough material that the streaming instability rapidly grows them to larger sizes, and so they no longer contribute to the optical depth that we're inferring. I think it's a really interesting story and an exciting one to follow up. But to do so, we need to understand what the gas is doing in order to concentrate those grains there. So the way that we can use the gas velocity structure to do this is to remember that the disk is in hydrostatic equilibrium. So because we're seeing radially this outward pressure gradient because the temperature and density are dropping as you move away from the star, that's going to support the gas against the gravitational potential of the star. If we now include perturbations in that pressure profile, say from a gap within the disk, as I'm showing on the top left panel here, that's going to induce a change in the pressure gradient felt by the gas, and that's going to induce a change in the rotational velocity. And that's what I'm showing you on the bottom panel here, that if we have a gap on the inner edge of the gap, you have a much steeper gas pressure gradient, and that's going to slow the gas even more relative to Keplerian. Whereas on the outside of the gap, you're now feeling a positive gradient, and that's going to accelerate the gas just outside the gap. Of course, you can flip this upside down. Rather than considering a pressure minimum as a gap, you can think about a pressure maximum, which is what we hope these grain traps are. And you can now go from a region where you have enhanced rotation to slowed rotation across the ring. And in this work with Giovanni Rizzotti, we're able to show that with the D-Sharp data, we could see that. So on the top right, I'm showing you the radial profile of the dust rings in HD 163296. On the bottom panel, the deviations in the rotational velocity. And you can see that over those three rings, we have this distinctive, faster, slower rotation profile, which allows us to infer the pressure structure of that disk and show that indeed those rings are being caused by pressure maxima within the system. With D-Sharp, we're only able to do this with two sources, HD 163296 and AS209. But for exoALMA, we could obviously go and do this for now a large sample of sources. So this was what Joe Stadler was doing. He was extracting the velocity profiles and trying to look at the structure within them. And really, we see in every single disk that there are significant variations in the rotation profile. None of them are purely Keplerian or even smooth. Some of them have deviations up to 15% of the relative background. So there's really quite a lot of structure within just these rotation profiles. And Joe was able to correlate the variations and identify the ones that are consistent with pressure maxima and show that over 75% of the continuum rings that we could resolve in our data are associated with pressure maxima. So I'd say that this number is probably going to be 100% when you improve the angular resolution, because you really need to push into the inner disk. But this work is really showing, I'd say rather definitively, that all the rings we're seeing are due to pressure maxima, and that is what is concentrating these grains into the structures that we see. The problem here, though, is that this technique is only sensitive to the pressure gradient. We have no idea about the actual magnitude of the pressure variations. We can just see the shape of the curve. Now, Tomohiro Yoshida was able to solve this in one of the cases when he looked at this really incredible disk J1604. So the dust distribution is shown on the right here, and it's this really wonderful narrow ring. You've got a huge cavity and this nice sharp ring exterior to it. And Tomohiro was thinking about the pressure profile here. We'd seen that the rotation profile gives this really nice pressure maxima profile across the ring. And he wanted to try and understand whether there's a way that we could normalize the pressure profile. And so he looked at the gas emission around this ring, and he took emission across the whole azimuth, stacked it all together. So he shifted it to account for the rotation profile of the disk, stacked it all together to get an incredibly high signal-to-noise ratio line. And that's what's shown in the top left panel here. So this black line is the observations of the stacked spectrum, and you can just see how high signal-to-noise it is. The wiggles in the line outside just tiny in comparison to the profile. And to this line profile, Tomohiro fit various sort of model profiles, including a purely Gaussian model, an optically thick profile where you get this sort of saturated core. And he found that when you really zoom into the wings at the very base of the line, you see these wings that just can't be explained by Gaussian at all. And he was able to show that the only way we could account for these wings was to include a level of pressure broadening at the same location, which gives you a non-Gaussian line profile. And based on the magnitude of those line wings, we're able to measure directly the molecular hydrogen density at this ring location. And so that allowed us to directly calculate the pressure profile, normalize it, and get the shape of it. So for a handful of disks, we're actually able to not only get the shape of the pressure profile, but we can see the amplitude and the variations. And this is going to really help us understand how efficiently grains are being trapped in these regions and whether they're being trapped efficiently enough to sort of build up the densities that we need to incite the streaming instability. It's not just radial variations that we can see this in. As I mentioned before, there are a handful of disks that show azimuthal variations. We have these really nice clumps in the continuum. And this was the subsample of sources that Lisa Wolfer was looking at. We had 4 within exoALMA, shown here. And I think what's particularly interesting about these sources is that the continuum dust distribution, so these large millimeter grains in the midplane, looks very different from the grain distributions traced by scattered light. So things looking at the sort of micron-sized grains in the atmosphere. You can see that the midplane is rings with some azimuthal clumps. The surface tends to be these sort of large spiral patterns. And so Lisa wants to understand whether these clumps were indeed sites of vortices which could be constraining and trapping grains azimuthally as well as radially. So as you might expect, by looking at the scattered light observations of these sources, the velocity structures in these 4 were incredibly complicated and a real pain to try and understand. So this panel here is showing you the velocity residuals of 12 CO on top and 13 CO, so on the same scale here. And the little black contours are showing you these azimuthal clumps in the continuum. And I think if you squint, you can convince yourself that there's sort of a spiral-like structure, but it's changing positive and negative signs along the spiral arms. There's maybe some annular structure going on as well. But I think what is relatively convincing is the fact that the 13 CO seems to be tracing very similar structures as the 12 CO where they overlap. And so that's suggesting that these are real variations in the velocity structure, and it's not just noise that we're inferring. So Lisa was running with Marcelo Barraza Alfaro a number of numerical simulations of vortices in these disks, trying to understand what velocity structure those vortices would reproduce. We tried originally to use simple analytical models, but those were really failing to explain the complexity that we're seeing here. And these left set of panels are showing you the best fit model that Lisa was able to find in the lower panel and comparing that to the 12 CO and the 13 CO residuals that you're seeing above. So it's not a perfect fit, but I think it does a really good job of describing sort of the bulk properties of the structure, the fact that we've got spirals, that we've got sort of red, blue, red residuals going on. And this modeling wasn't in any way fine-tuned to match this specific source. We just took a generic disk, put a vortex in at a certain radius, and then reprojected the disk so it's at the same inclination and position angle as H2135. And so I think this gives a lot of evidence to the idea that we do see evidence of vortices in the system, and it's vortices that are creating this azimuthal dust trapping. But I think there's still a lot of work to do in terms of understanding how constraining those pressure traps are in terms of trapping the dust. But this doesn't really explain what's driving the vortex. We can see that there is a vortex in this system, but what's driving that? And so Marcelo Barraza Alfaro was looking at whether we could use the velocity perturbations that we extract from the data to point towards a specific magnetohydrodynamical instability that's driving it. And so Marcelo has a whole range of different instabilities we can look at, and this is an example of comparing the MRI, the magnetorotational instability, with the VSI, the vertical shear instability, where what's plotted is the velocity broadening, so the non-thermal microscale turbulence in the disk. And you can see that the VSI leads these very sort of nice annular structures, very narrow rings of enhanced turbulence, whereas the MRI is perhaps a bit more chaotic. It's got spiral arms in there, and we'd hope that we can differentiate between these two. And so Marcelo was able to run a whole load of different radiator transfer simulations to explore what these instabilities would look like. And so these are 3 of the ones that he was looking at. Again, you can see that the VSI gives this really nice corrugated sort of structure. The magnetorotation instability in GI gives spiral arms, but there is some sort of difference in the magnitude of the spiral arms and the number of them and so on. So the hope was that we could use this gallery as a way to piece together what instabilities we see in the disks in our sample. Unfortunately, it really wasn't that simple, and basically none of the disks that we looked at out of the 15 that we had showed anything that really resembled any of those models. You can see some of them showed these really large spiral arms. J1604 in the center did show this sort of annular structure, so that might be evidence of the VSI, but only seeing one of them rather than a set of nested rings suggests it's probably not the VSI that we're seeing. And then a lot just sort of looked noisy, like on the right-hand side. There was just too much structure in there to really pull out a lot of information about what's driving that instability. And so in wave 1, we've sort of left this for now. There's a lot of work to do. And the wave 2 papers, which are coming out later, is really going to focus on the 2D structure of these velocities and trying to better understand what they're telling us. There is hope, though, and I think just as a point of comparison, while we don't see any evidence of sort of large-scale instabilities that point specifically to a certain process, there are sources that show this. So this is really lovely work led by Jess Speedy looking at A.B. Arriga, and she's shown that in the velocity structure there, when you subtract away a smooth Keplerian map, you get these really nice spiral arms that are really a good match to the gravitational instability. So for some reason, the GI is very obvious in A.B. Arriga, but for the 15 sources we have as part of exoALMA, it's not quite clear at the moment what's driving those instabilities. So in terms of the methods, I think, again, we've made huge progress in being able to leverage the pressure profiles of these disks to confirm that we are concentrating dust grains in pressure maxima both radially and azimuthally. We do see a huge amount of perturbations within the disk, so we see that large-scale instabilities are working within there, and it's probably these instabilities that are driving those pressure maxima. But we're having a hard time backing out which of those instabilities are going to cause the structures that we see. I think there's going to be some work to do there. So the final step of the first wave of papers is really looking at the outcome. What sort of planets does this make? And I think here, again, there's a lot of work to do. So this is a relatively short section, but there's going to be a lot more in wave 2 coming along. So one way that we can try and understand what sort of planets are within these disks is looking at how those planets sculpt structures within the disk. And Charlie Gardner led a work looking at specifically the calcium-15, where we now have incredibly high resolution continuum and gas observations. And he was able to understand what planets are consistent with the gas and dust morphologies that we see, and whether those planets are indeed consistent with the direct detections that people have published in the literature. And basically, we need relatively low mass planets in order to create the structures that we see, but not have them be too large that we would detect any azimuthal variations in the dust, as you can see over here in the lower right panel. The most direct way of detecting these planets would be to detect circumplanetary disks like PDS-70c. If you see a nice dot in a cavity or a ring, then that's a surefire way of saying there's a planet there. But this is exceptionally hard to do. So Pietro Pironi looked in great detail at the 15 continuum data sets that we had, saw wonderful amounts of structure, but there was no real obvious evidence of circumplanetary disks, at least in our data sets. Although we went really deep to look at the gas, we didn't have a huge amount of bandwidth dedicated to continuum. So these aren't really super deep continuum observations. You can really do a much better job with a dedicated program here. So I don't think the lack of CPDs is really too constraining from our data. The other way that we've been trying to infer planets is based on their influence of the gas dynamics. So in TW Hydra, we've found that there's this really large sort of single arm spiral emanating from a region of disk where we know there's a large gap in the scattered light. And so the argument here is that it's probably a planet which I think we argue something around a Neptune mass planet would be able to open up the gaps that we see in scattered light and also drive potentially this spiral arm. Not all of the planets would be expected to create such a nice structure in there. I would imagine many people here are familiar with the idea that what we're looking for are actually kinks in the emission morphology. And that comes from the fact that the planet that's embedded in the gas disk creates these shock fronts, which drive this spiral wake. And because one side of the spiral is rotating faster than the background, and the other side is rotating slower from the background, that's going to cause a break in your isovelocity contour, which you should be able to see in your emission morphology. So this is a model of HD 163-296 where we think this is happening. And that sort of break, this thunderbolt pattern, is due to that sharp change in velocity structure as we move across the planet. So Christoph Bunt sort of led his paper, was trying to find these features. He goes into gory detail in his paper about all the different velocity structures that we see. And I think there's a huge amount. Every single source shows something in there. He's whittled it down to 6 that he thinks have planet-looking signatures. 5 of them are new. We haven't seen them before. 1 of them he'd already found from T-sharp data. And this is just a gallery of the locations of where he finds those velocity perturbations and where he would need to place a planet in order to explain the velocity structure and also account for perhaps some of the structure that we're seeing in the overall distribution of the gas. This, I would say, is still early work. There's a huge amount going on now trying to do this more quantitatively and more in a reproducible way rather than just looking at the data by eye. And so many of those works are going to come out with Wave 2. So with that data set, we're able to constrain or sort of provide circumstantial evidence for where planets should be based on the gas and dust distributions. We don't see any clear evidence of circumplanetary disks, but as I say, the data is not really taken for that, so I wouldn't weigh that too much. We see a huge amount of velocity structure in these disks. We would argue that perhaps 6 of them show the features consistent with embedded planets. And we've got many other works trying to do this in a more systematic way. And of course, we've got lots of direct imaging campaigns to try and find other evidence of these planets based on sort of their optical emission that we're seeing. So to just wrap up those 3 main points, as I say, this is really trying to condense all those 17 papers down into a couple of themes. So there's a lot more in the papers. But in terms of ingredients, we've been really able to, I think, make a step forward in our ability to measure gas masses in these disks based on dynamical masses. And we can understand how to use these to better calibrate the mass measurement techniques that we need to apply to populations on the whole, because we can't do dynamical masses for everything. We can see that all the disks are incredibly dynamic. We can see that creating pressure perturbations, which are indeed trapping dust. But it's not clear at the moment what the specific instabilities are that are driving this. I think there's a lot of work to do there and try and make sense of the structures that we're seeing. And we can also say that a lot of the structures that we see in the disk are reminiscent of those that we'd expect to be produced by planets. So again, I think there's a lot more work to do here in both modeling, making predictions of what planets should be causing, and doing a better job of extracting those features from the data and isolating them. And a lot of that work is going to come out in the second wave of results. We're hoping that this is going to be something that comes out later on in the year. We've already had a collaboration meeting at the start of the year to get work on that. But in the meantime, all the data and the scripts that we've used for those first wave of papers, all the raw data is available on our website, exoALMA.com. So we have the fully calibrated measurement sets, all the imaging and calibration scripts, all the data, all the images ready to go. So we'd really encourage you to go and have a look at that data and have a play with it. And if there's something that's wrong with it or there's missing, please let us know so we can make sure that that's uploaded for you. And with that, I'm happy to take any questions, and thank you for your time.
Thank you, Richard. Amazing program. If anyone has questions, please use the raise hand function at the top of Teams, or leave a message in the chat box. So, any questions? Don't be shy. In fact, Richard, I have questions that about SNA is exoALMA 11 or 9 is about ITC 15, because I remember we know ITC 15 has a dust cavity, but you didn't observe the gas cavity. So what do you think of this?
So I think it's trying to model the gas is really tricky at these sort of resolutions. So I would say that there is sort of evidence of a gas depletion in the inner region, but it's not as significant. And it's that lack of depletion that's really creating this argument that there can't be massive planets there. I think that our ability to trap grains perhaps is more efficient than we have given it credit for. So that might be a reason that we're sort of able to create a very enhanced cavity in the dust without depleting the gas so much. But it's definitely something that we want to go back and look at in more detail. I'd say that the images that Charlie was able to produce for that paper were really fantastic, and they could get exquisite angular resolution. But to do that, they had to really bin down the velocity resolution, and that's really crucial for those inner regions. So I think there's a lot of work to do there in sort of getting just high angular resolution data to really probe that cavity better.
Okay, thank you. Yeah, Greta, please propose your questions.
Yeah, thanks, Richard, for a very nice overview. I was wondering, you said at some point that 75% of the rings seems to be associated with the pressure traps. What about the remaining ones that are not? Do these disks or rings have something in common, or it's just a matter of sensitivity?
I think it's nearly all a resolution effect. So you can push down to higher angular resolutions for the dust, so we see a lot more rings than we can really analyze with our gas. So I think the continuum resolution was maybe a factor of 3 times better than our gas. And so all the inner regions and the cavities, for example, we couldn't really access with that data. So I would say it's likely that it's just a resolution effect.
It's just sensitivity, yeah. Okay, thanks.
Okay, maybe using first, and then yeah, using, please.
Hi there. Very nice talk and great data, a great analysis. I have a question and a comment, and a question that is linked to a comment. The first question is, you mentioned that you had an idea, you were able to measure the absolute value of the pressure with the method that you proposed in that ring. But maybe you said that, but how much pressure, what the value of the pressure, what is the range of the pressure that you measure? And the second question is mostly, I noticed that your dynamical masses for the disk are very in a narrow range. I mean, more or less are always 0.1, 0.15. If this is due to the sample, I don't know the sample, or really we say that we can see that different disks selected in different way are more or less the same disk masses. So if you can comment on that, honestly, I don't know well your sample, so.
So in regards to the first question, I can't remember off the top of my head what the pressure is. I'd have to look. I do remember that it was nothing crazy and sort of consistent with what we would expect based on standard disk models. For the second one, you're right, they all do cluster. And I think that's, as you mentioned, a purely sample bias. This bias is hugely sampled. We chose the biggest, brightest disks that basically weren't covered by maps, because our argument was we wanted to demonstrate what you can do when you have this quality of observation. And so the biggest, brightest disks were the ones that we had to go for. And I think sort of getting up to this range is about the upper limit to the mass that you can get before it tears itself apart. So it's sort of, I think we're just looking at that tail end, and it's purely a sample selection effect. As I say, both Sean Andrews and the Milan group worked really hard to look at a variety of disks, and they both came to the same conclusion that we can do this accurately and precisely with lower mass disks. It just seems like we didn't have them in the sample by chance.
Thank you very much.
Okay, Luna, please.
Hi, Richard. Thank you. It's really great to see all these beautiful results coming out. So I have more a general question. So you showed correlation between substructures in the continuum observations and, for example, pressure maxima, or correlation between kinematic deviations with the like continuum over brightness. So
Yeah.
I was wondering also if you see correlation between deviations like in the velocity field or in the line width and structures in scatter light, and if there is also any correlation with the like chemical signatures in other tracers that we can access. Maybe you showed also something at the end of the presentation, but I may have missed if it was a scatter light observation. Sorry.
Yes, I think that's a really good question. Essentially, we haven't looked at that in detail. That's work that we're doing at the moment. I think in terms of scattered light, that would be a really interesting project. Someone had signed up at the start to do that, but then people just got too busy to look at that. So I think that would be a really interesting thing to look at. It looked like the velocity structures do correlate in some way between all the continuum rings, but I think the issue that we found was that it's much harder to characterize the structures that we're seeing in the gas velocity structure compared to, say, the emission morphology, where you could basically say, here's a ring and here's a gap. The velocity had so much azimuthal structure that it didn't make too much sense to just azimuthally average everything. And so this was really why we've had to split the publications into wave 1 and wave 2, because those wave 2 ones are really trying to deal with that azimuthal variation as best they can. So I think that's something that's going to come out in the next couple of months as we get a better handle on how to deal with it. But I'd agree with you. I think that's where there's going to be a lot of information about what's causing these structures, is the correlation between different traces.
Thank you very much.
Okay, does any questions? If we haven't other questions, let's thank Richard.